pattern. Hello and welcome to another video of the Grokking the Coding interview series. We're going through the depth first search pattern, and in this video we'll have a look at all paths for a sum, which is classified as a medium problem. Again, it's slightly related with the previous problem we worked on, so if you've not checked out that video, I strongly recommend to have a look at that video as well. Why I wanted to cover this problem is because the space and time complexity approach is very interesting for this one. So let's try to understand what the problem requires us to do. Given a binary tree and a number s, find all the paths from the root to leaf such that the sum of all the node values of each path equals s. So we have a binary tree. We have to find all the paths which add up to a number s. So in this case, s is 12, and we see that 174 and 192 add up to that number, and hence we have to return this as the output here. And again, we have an example here where we have the s is 23, and we have to return 1274 and 12110 as the path which add up to that number s. So how would we approach this problem? We already looked at how to traverse such trees in depth first search approach. And essentially what we want to do in this case is we want to go through each of the paths, and as soon as the sum adds up to s, we will push this path into a results list. Essentially, there are two components into the way we traverse it. So for each path, we have to keep a track of all the nodes comprising of that path. So when we are traversing a single path, until and unless we have validated or invalidated that path, we have to keep a track of all the nodes. So, for example, I have to keep a track of 175 until I've invalidated that they add up to S. And what I also have to do is once I'm, say, here 174, and I want to keep a track of the current path, for example, and I go and I return to 7 again, then I have to make sure that I'm removing the final node from this path as I'm transitioning to the other one. So say once I explore until 174, and now I'm back and I've backtracked at 7. I want to remove 4 from this path and continue my exploration for 175, for example. So there are a couple of additions from the previous algorithm implemented during traversal. There we only have to find any existing path and return true. Here we also have to return the path, and that would be the main difference. So let's see how we can go about implementing a solution in this case. Let's make sure that we have enough space. So I'm going to go ahead and define a couple of variables here. So I have a current path, just for the sake of cleanliness. It will also be a list. And I will define another variant of this function, which I'll invoke from here. Recursive, where I'll provide the root node, which will be the current node. I'll provide the required sum, which will be this sum, which we have. I'll have to provide the current path as well as all paths. So these are the things I want to provide in this function call. Let's go ahead and define that function separately. In this case, find paths recursive. we want the current node, we want the required sum, we want the current path, and we want all paths. So let's try to implement the initial sanity checks which we need to run. So if the current node is none, we simply return at this point. We want to append the current node into the current path or the value of that node. And we want to check if the value of, first we want to check if the current node is a leaf node and if the value of the current node is equal to the required sum. If this is the case, that means that we have encountered a path which adds up to s. So if current node dot value is equals to required sum and current node dot left is none and current node dot right is none, in that case we will go ahead and append this path into the all paths list. Okay, else we continue our traversal as usual, which will be find paths recursive, and here we have to provide the left side of the current node or the left subtree of the current node. We want to provide required sum minus the value of the current node, and we have to provide the current path as well as all paths, and this should be fine. And we'll just run the same thing for the right subtree as well. Which will be just right. So either at this node we have encountered a leaf node and the value adds up to the required sum. In that case, it means that we have encountered a path which adds up to s, and we just append it into the list of all paths here. Otherwise, we just continue our search and we provide the current path as well, so we can append more nodes into it. Now, once we have finished our recursive call and we are process of backtracking, we want to return, we want to remove the final node from the current path. So, for example, as we spoke about it here, once our exploration is complete here and we start backtracking, in order to maintain or keep the current path updated, I want, once I hop from 4 to 7, I want to remove 4 from the list of current path, and it is exactly what I'm accomplishing here. So I'm removing the final element from the current path. And this should essentially give me the answer I'm looking for, unless I've made some specific mistake. So let's try to run it and see if it gives us what we expect. And essentially, in this case, what we want is 12, 7, 4, 12, 1, 10. Let's run it. 12, 7, 4, 12, 1, 10. Okay, so seems like our implementation is correct. In case you have identified something that I might have missed, please let me know in the comments. And this would be a good occasion to speak about the space and time complexity of this implementation, because I was going through it and I found it a bit confusing and interesting at the same moment. So let's speak about it. And what we'll also try to do is we'll try to address it more and more in the next question, so we have an understanding of how to approach space and time complexity in such problems. Okay, so the the time complexity of the above algorithm is O of n squared, where n is the total number of nodes in the tree. This is due to the fact that we traverse each node once, which will take O of n. And for each leaf node, we might have to store its path by making a copy of the current path, which will take O of n. So this dimension, honestly speaking, is not that clear for me. Like how storing something would contribute to the time complexity of the algorithm. However, again, as I said, I'll try to make it more clear as we go through the examples. I'll also explore lead code and other explanations. And if I find something which is more concrete, I'll make sure to share it with you. We can calculate a more optimal time complexity or n log n from the space complexity discussion below. So let's speak about the space complexity of this implementation. If we ignore the space required for all paths list, the space complexity of the above algorithm will be O of n. In the worst case, the space complexity will be used to store the recursion stack. The worst case will happen when the given tree is a linked list. How can we estimate the space used for the all paths array? Let's have a look at this example. Take the example of the balanced tree. Here we see we have 7 nodes, since for binary tree there exists only one path to reach any leaf node. We can easily say that the total route to leaf paths in the binary tree can't be more than the number of leaves. Okay, as we know that there can't be more than n plus 1 by 2 leaves in a binary tree. Therefore, the maximum number of elements in all paths will be O of n. And we also know that each of those elements can, at max, have. Um, Now, each of those paths can have many nodes in them. For a balanced tree like above, each leaf node will be maximum depth. As we know that the depth of a balanced binary tree is log n, we can say that at the most, each path can have log n nodes in it. This means that the total size of all paths list will be n log n if the tree is not balanced. Okay. Okay, so we saw that the time complexity for this implementation is O of n squared, and the space complexity is O of n log n. We could optimize it further, call it O of n log n. But again, I have to accept that I've not understood it fully. So as I find more clarification around it, I'll share it with you as well. I hope you enjoyed the explanation so far. Please let me know if you want me to improve any dimension. We'll be more than happy to address your questions. Until the next video, have a great day.